Hi, Tim Wilhelm here from Kankakee Community College's IREC accredited solar training program. The reason we're here today is to discuss calculating the spacing for sawtooth photovoltaic arrays. This is a competency in the NABCEP task analysis for anyone seeking NABCEP installer certification. I want to make a point though, starting with a small story. There's an old story about engineers. Engineers measure with a micrometer, then they mark with a piece of chalk, and then they cut with an axe when they're finally done. And the reason I share that story is because there's two aspects of this idea of spacing sawtooth arrays. One is the mathematical precision that an engineer would use in laying this out to make sure that you space the subarrays exactly at the distance that you've calculated using multiple trigonometry calculations. The other side of this is that in the real world, you're going to chop it with an axe. There is a 3-station sawtooth array on this pergola right here. And these are spaced way further than they need to be for shading that would occur at 9 a.m. or 3 p.m. on the winter solstice when the shadows are long. However, there's not enough room to fit 4 up here. So if we wanted to use the exact trigonometric calculation, the calculated distance, and pull all these in, it would look like something's missing. Another part of doing solar installs is making sure that things are aesthetically pleasing. So 4 wouldn't fit, squeezing it down, so you space them out so it's nicely done. You got plenty of room, no shading worries, and we didn't have to do it according to the precise mathematical calculated distance. That said, NABCEP wants you to know how to calculate that distance. Now, one thing that has created some confusion in the industry is that NABCEP published a study guide for the NABCEP professional installer exam. And in that study guide, they gave an example. At 30 degrees latitude for the position of the array, they had a rack like this. This is not the rack from the example. That rack had a 3-foot distance right here. And they said, calculate the correct spacing between this array and the next subarray so that there's no shading on the northernmost rack at noon at 30 degrees latitude. Well, at noon, the sun is higher in the sky, the shadow is shorter, and a number of people assumed, oh, that's just how you do it. Let's just find the noon elevation of the sun. Let's just do a nice, flat, 2-dimensional drawing of triangles. Let's lay our triangle out. We know we've got 3 feet here. We know the angle of elevation at noon. Let's calculate that distance and put the next array, subarray right there. The problem with that is that the shadow within our solar window between 9 a.m. and 3 p.m. gets longer than that, because at 9 a.m. when the sun comes up, the sun is lower. At 3 p.m. late in the winter when the sun's getting ready to go down, the shadow is longer because the sun is lower. We actually need to space longer. So instead of being a single trig calculation, this becomes 2 trigonometry calculations. So let's go through how you would approach this. Right here in my carpenter pants pocket, I have, using the example from the NABCEP exam, I have a sun chart for 30 degrees north latitude. Do you see that up in the corner of the screen here? Now, what I want you to see is that there are times listed on here in somewhat vertical arcs. We have what's called the solar window from 9 a.m. to 3 p.m. that we want to make sure we don't have any shading during that window. We do not want this guy to cast any shadow on that guy between 9 a.m. and 3 p.m. That's when we get the bulk of our solar irradiation collected for the day, is between those 2 hours. So we want to take our absolute worst case situation for the year. Our worst case situation is going to be either 9 a.m. or 3 p.m. on the winter solstice, when the sun is absolutely at the lowest point in the sky. So what we do is we get our sun chart like this, and we find the arc of the winter solstice, and we find the 9 a.m. mark, and where those two intersect, we can go across to the elevation mark on the side, and we see that at 30 degrees latitude at 9 a.m. on the winter solstice, the elevation of the sun is approximately 22 degrees. That means 22 degrees up above the horizon is where the sun is. However, there's something else going on here, which is azimuth. If this is facing straight south and we're using solar azimuth as opposed to compass azimuth, straight on like this is 0 degrees. But the sun is not at straight south at 9 a.m. in the morning, it's off over this way. How do we find that? We go again, check the chart in the corner, we go again to the winter solstice arc, we find the bottom end of 9 a.m. and we come straight down, and we see that we are 45 degrees over from the south. So the sun is at an azimuth of minus 45 degrees to the east, and up at 22 degrees above the horizon. We need those numbers to be able to start to lay out triangles so we can calculate what is the minimum distance between these two subarrays in this sawtooth racked array, so that we don't get any shading during the critical solar window on the winter solstice. Step one in figuring out this proper distance calculated between the subarrays of our sawtooth array, we have to acknowledge that at 9 a.m., here we are on the winter solstice, late December, December 21st, the sun is off at 45 degrees to the east, and it's at an elevation of 22 degrees. The sun coming in from that position is hitting the top of this first rack of the sawtooth array, and it's casting a shadow down this way. That shadow can be used, that line can be used as the hypotenuse of a triangle. Now we know that the sun's elevation is at 22 degrees. That means that where the sun hits down here, that hypotenuse hits, that's 22 degrees above the horizontal. Opposite of that 22 degree angle, I have right here the opposite side. In the NABCEP study guide practice problem, that is a distance they give of 3 feet. There's also an unknown distance that comes from here, 90 degrees off of the opposite side. We have the adjacent side going over to the vertex of that angle right there. So this is an unknown distance we'll label D. We want to solve for that distance right there. We use a little trigonometry for that. We have two knowns. We know an angle, we know an opposite side. Our unknown is the adjacent side. So we will use the tangent of that angle. The tangent of 22 degrees is going to equal the distance of the opposite side divided by the length of the adjacent side. So I have the tangent of 22 equals 3 divided by D. Shuffling the equation over here, I can solve for D, and I see that D, this distance here, this unknown, equals 3 divided by the tangent of 22 degrees. I don't have a calculator in my brain, but I think if we calculate that out using the numbers from our 30-degree latitude sun chart, and we use the 3 feet, I think we end up with something over 7 feet for this distance right here. Now, that though is the distance from here to here off at a 45-degree angle. It's not the distance straight back to the next subarray. If we were to just use that 7+ feet, that would be back much further than it would absolutely need to be. So we have a second triangle that we need to do a calculation for. Here's our second triangle. Our first triangle was vertical. Our second triangle is going to be flat on the floor. It's a horizontal triangle. I'm still using the point where the shadow line comes down to the triangle down here. Now I have a different angle though. The angle I have now is 90 minus my solar azimuth. Well, it's good and easy in this case because with solar azimuth at 45, 90 minus 45 equals 45. So now from where this line came down and I had my 90-degree angle here, that's going to be also the point of my second flat triangle. It's going to run from here and follow D. So what was D in the first problem is now the hypotenuse for the second problem. My angle is 45 degrees. My adjacent line, I don't care about. What I care about is my opposite line, my opposite side right here. So I've got now a triangle that goes like this, and back over here. That angle is 45 degrees. I know the length of the hypotenuse because I already calculated it. It was about 7.25, 7+ feet. Now, how can I find this? If I think back through my trig functions, I remember that the sine of an angle is the opposite divided by the hypotenuse. So now I know that I have sine of 45 degrees equals my unknown divided by the 7+ feet that I calculated in the first problem for that light right there. So now I want to solve for the opposite side. By shuffling the equation again, I find out that this length right here, that opposite side, equals the hypotenuse times the sine of 45 degrees. When I run that calculation, I find out that the length of that opposite side is 5.25 feet approximately, a full 2 feet shorter than the first calculation. So now I can bring that in to about 5.25 feet, and at 9 a.m. I will not have a shadow on this rear array on the winter solstice when the sun is lowest in the sky. But let's go back to the story of the engineer measuring with the micrometer, marking with a piece of chalk, and cutting with an axe. There's ways of fudging this and doing it simpler and easier with one single calculation. Let me give you an example, and you'll have to play with this for your specific latitude that you're working at. With the 30-degree latitude, instead of using 9 a.m., if I use 10 a.m., with an azimuth of 0 degrees, so I take my 10 a.m. elevation and just do one calculation, similar to the first calc we did before, I end up with 5.2 feet instead of 5.25 feet. You know what? That's cutting it with a piece of axe. Like cutting it with an axe, marking it with a piece of chalk, it's close enough. So sometimes you can figure out a way for your specific latitude where you don't have to do two calculations. If you know you're always at 40 degrees latitude, find the elevation of the sun and the time of day that gives you the same result as doing the two calculations at 9 a.m. And you can get this down to one single calculation that's close enough for real-world applications. Thanks for watching. And if you'd like more information, you can log on to www.kcc.edu/RES, Renewable Energy Stuff. When you get there, look for links to YouTube videos, and you can subscribe to our YouTube channel, and you'll be informed as more instructional videos are developed. Have a great day.